What is a diode? A diode is a two-terminal electronic component that allows current to flow in only one direction. A diode acts like a one-way valve for electricity. It has two terminals, an anode, which is the positive side, and a cathode, which is the negative side. The fundamental property of a diode can be compared to a one-way valve. In the forward direction, current can flow through. But in the reverse direction, current is blocked, just like water cannot flow backward through a one-way valve. Diodes are made from semiconductor materials, typically silicon or germanium. The unique properties of these materials allow diodes to control current flow. In a circuit, when the diode is forward biased with the anode connected to the positive terminal and the cathode to the negative, current flows through the diode and the rest of the circuit. However, when the diode is reverse biased, with the cathode connected to the positive terminal and the anode to the negative, current cannot flow. The diode blocks the current in this direction. To summarize, a diode is a two-terminal semiconductor device with an anode and a cathode that acts like a one-way valve for electricity. It's typically made from silicon or germanium and conducts current in the forward direction while blocking it in the reverse direction. The current voltage characteristics of a diode demonstrate its nonlinear behavior. We can divide the IV curve into two regions, reverse bias and forward bias. In reverse bias, where the voltage is negative, the diode allows only a minimal leakage current to flow. In forward bias, once the voltage exceeds the threshold voltage, the current increases exponentially. This behavior is characteristic of diodes, which allow current to flow easily in one direction but block it in the other. The Shockley diode equation mathematically describes this nonlinear relationship. The equation relates current to voltage using several parameters. Is is the saturation current, V is the voltage across the diode, N is the ideality factor, and Vt is the thermal voltage, which is about 26 millivolts at room temperature. As the voltage increases beyond the threshold, the exponential term dominates, causing current to rise dramatically. Understanding these IV characteristics is crucial for designing circuits with diodes and predicting their behavior in both forward and reverse bias conditions. Diodes come in various specialized types, each designed for specific applications. Rectifier diodes are the most common type, used primarily to convert alternating current to direct current. Light-emitting diodes, or LEDs, emit light when forward biased. Different semiconductor materials produce different colors. Zener diodes operate in the reverse breakdown region without being damaged, providing voltage regulation and protection in circuits. Schottky diodes use a metal semiconductor junction for faster switching and lower forward voltage drop, making them ideal for high-frequency applications. Photodiodes convert light energy into electrical current. The amount of current generated is proportional to the intensity of light. Varactor diodes exploit the variable capacitance property of reverse-biased PN junctions for frequency tuning applications. Let's compare the key properties and applications of these different diode types. Each diode type is optimized for specific characteristics by modifying the basic PN junction structure to excel in particular applications. Diode parameters and specifications are critical for selecting the right diode for your application. Let's examine 6 key parameters that define a diode's performance characteristics. The forward voltage drop, or VF, is the voltage required for a diode to conduct current. For silicon diodes, this is typically around 0.7 volts. Different diode materials have different forward voltage drops. Germanium diodes have about 0.3 volts. Schottky diodes range from 0.2 to 0.3 volts, while LEDs can require 1.2 to 3.5 volts depending on color. Maximum forward current, or IF, is the highest current a diode can safely handle. Exceeding this limit can cause permanent damage due to excessive heat. Standard diodes typically handle between 1 milliamp and 3 amps, while power diodes can handle hundreds of amperes. When this maximum current is exceeded, the diode generates excessive heat and can fail permanently. Reverse leakage current, or IR, is the small current that flows when a diode is reverse biased. Ideally, this would be zero, but in real diodes, it's not. This leakage current is typically very small, in the nanoamp to microamp range for silicon diodes. It increases with temperature and varies by diode type. Reverse breakdown voltage, or VBR, is the voltage at which a diode in reverse bias suddenly begins to conduct large amounts of current. Most standard diodes have breakdown voltages between 50 and 1,000 volts. When this voltage is exceeded, the diode enters breakdown, and current increases dramatically. Operating a diode in breakdown can permanently damage it if the current isn't externally limited. However, Zener diodes are designed to operate safely in this region. Recovery time describes how quickly a diode can transition from conducting to non-conducting state. This is critical for high-frequency applications. When a diode switches from forward to reverse bias, it doesn't stop conducting immediately. The time it takes to stop conducting is called the reverse recovery time. Standard diodes have recovery times from 100 nanoseconds to several microseconds. Fast recovery and Schottky diodes are much quicker, with recovery times under 100 nanoseconds. Junction capacitance is a parasitic effect that occurs at the p-n junction. The depletion region acts like a dielectric between two plates, forming a small capacitor. This capacitance typically ranges from 5 to 200 picofarads, depending on the diode type and size. Schottky diodes have lower junction capacitance than standard p-n diodes. Junction capacitance becomes problematic at high frequencies, limiting the diode's performance by distorting signals and increasing switching losses. Let's summarize the key diode parameters we've covered. These specifications are critical when selecting the right diode for your application. Understanding these parameters will help you select the right diode for your specific application, ensuring optimal performance and reliability.